All right, hey guys. We are starting day one of probability units. This is our first day of this next unit. This is our second to last unit. We got this, then statistics. All right, so we've probably all heard of probability before. I'm not sure how much of y'all have actually learned any probability in math classes before, so we're just going to start with the basics here. Um, Probability has to do with the chances of something occurring. Right? That's what this whole unit is about, is identifying the probability of something happening. Okay, we'll stick with basic examples, the most common examples, that kind of stuff. All right, now in order to figure out the probability of something happening, we need to know how many times something can occur. Okay, know the outcome of certain events happening, the number of things happening. All right, if we know the number of things happening, then we can figure out the probability. All right, so these next 2 days are going to be spent on counting. It's a little bit more complicated than just saying counting, but that's pretty much the basics of how it works. Okay. Now, before we start talking about counting, we need to discuss sample space. All right, whenever we're talking about probability, we need to know what's in the sample space of the things we're trying to find the probability of. All right, so sample space. What is sample space? An outcome is the result of a single trial. Okay. Whenever we're in probability, we're going to be doing something. Okay. What's the probability of us rolling a 6 on a dice? Okay. What's the probability of us drawing a card? What's the probability of something happening? All right. That's called a trial. That's a single trial. Now the outcome is the result of that trial. That's what we're going to be trying to identify. An example: the trial of flipping a coin has two outcomes. Heads or tails. If I were to flip a coin one time, the outcome is either going to be heads or tails. All right, so your sample space would then be heads or tails. Okay. The set of all possible outcomes is the sample space. Kind of what we just said with that coin example. The sample space is heads or tails. Two different outcomes. All right, with another example with rolling a six-sided die. All right, we have 6 possible outcomes. Right, it could either be 1, 2, 3, 4, 5, or 6. All right, the sample space is all those numbers. Now, with sample space, if you have more than one of the same thing in the sample space, we only list it once. Let me give you an example. Let's say that we want to know the probability of selecting a letter from the word Mississippi. Mississippi. All right. All right, that's a lot of letters, and it's also a lot of repeating letters. All right, so our sample space is only the letters that are there without repeating. Okay, so our sample space is the letter M, the letter I, letter S, and the letter P. Okay, so only those 4, not all of the repeating letters. Okay, so that's about as crazy as it gets when identifying your sample space. All right, let's do some examples of finding the sample space. Oh, God. I have one student here right now, it's Keaton, and he just keeps looking at me. So,
Hey, class.
Hey, class. All right, so just pay attention. Just pay attention. All right, practice. Give a sample space for each experiment. So drawing a card from a deck containing only the 13 hearts. Now, I know a lot of people in here probably have, well, not a lot, but some people might not know or anything about a deck of cards. And actually, a lot of our questions have to do with a lot of deck cards and stuff like that. So I'll always give you like all the outcomes in a deck of cards. I'll put that on the board for the test, so don't worry about that if you don't know it. But anyway, the sample space here would just be all the different outcomes you can have if you are selecting a card from a deck that has 13 hearts. So that would be, for example, the ace of spades, the 2, 3, 4, not spades, ace of hearts, 2 of hearts, 3 of hearts, 4 of hearts, 5, 6, 7, 8, 9, 10, jack, queen, king. All right, in a deck of cards, you have 4 suits. But in a deck of cards, you have 4 different types and 13 of each of those types, so there's 13 hearts. ace through king. But anyway, that's an example of a sample space. All right, how about tossing a coin 3 times? So the sample space, all the different outcomes you can have whenever you're tossing a coin 3 times. So it's not like our last example where it was just heads or tails, because that's only flipping it once. So if you flip a coin 3 times, here's all the possible outcomes. You could hit heads every single time. Heads, heads, heads. All right. You could have all tails. All right, and then you can have a bunch of different orderings of heads and tails. Right? You can have heads, heads, tails. Let's see here. Heads, tails, tails. And I'm going to have to think of the rest as we go. And honestly, for the sake of space and time, you can finish it on your own. There's quite a few of them, but that's kind of the point, right? Okay, so there is a lot of outcomes that could possibly happen with flipping a coin 3 times. All right, number 2, for each sample space, write the set that represents the given sample space, rolling a die. All right, event 1, the die is even. Well, if the die is even, the sample space is all the even numbers, right? 2, 4, and 6. The die shows a multiple of 3. What are all the multiples of 3 on a die? Just 3 and 6. Okay, so there's an example of sample spaces with certain criteria. Okay. All right, the set of the sample space where the die shows a 1. Well, of the 6 options, there's only one time that happens. It's when the dice is on a 1, right? The die shows a number less than 4. Okay, well, all the numbers less than 4 are 1, 2, 3. All right, so I don't want you to overthink sample spaces. Sample spaces are not that big a deal. It's just listing all the possible outcomes in some type of trial, okay? Whether it's rolling a dice, whether it's drawing a card, just understand what the criteria is and just write out all your possible options, okay? We need to know all the possible outcomes we can have before we can start finding probability. All right, when we talk about, okay, trial is doing something, all right? Now, a bunch of trials is called an event. An event consists of one or more outcomes of a trial. Okay? There are 2 types of events. You've probably seen these before. There are independent events and dependent events. All right, 2 events are independent if the result of the second event is not affected by the results of the first event. Okay, so like I said, an event is a bunch of different outcomes of a trial. So let's say like one event is me flipping a coin, and the other event is me drawing a card from a deck of cards. All right, those 2 events are independent of each other because they don't affect the other. All right, here's another example. The letters and digits on a license plate. Each letter or digit chosen does not affect the choices for the others. Okay, so it doesn't matter what letter I chose or what digit I chose, they do not affect each other. Okay, so that means they're independent events. 2 events are dependent if the outcome of the event does not affect the outcome of, or does affect the outcome of another event. All right, so let's look at this example. Taking a marble from a bag and not replacing it, keyword here, not replacing it, we're going to see that a lot, and then taking out a second marble. This is saying, what is the probability of picking a blue marble? All right, we'll talk about probability on a later day. Look at this visual. These are 2 dependent events. All right, the first time, taking a marble from the bag, I get a red marble. Okay, this bag looks like it has 2 blue marbles, 3 red marbles. All right, well, I have a 2 in 5 chance of picking out a red marble. Okay, if I were to select it the first time and pick a blue marble out, okay, then I'd have a 1 in 4 chance of picking a blue marble the second time, or a 2 in 4 chance of picking a blue marble the second time if I picked a red marble. Okay, so it depends on what I picked the first time. Makes sense.
Yes.
All right, let's look at some examples of independent and dependent situations. Wow, wow, wow. All right. Are the following events independent or dependent? I mean, these are common questions, common scenarios that y'all might ask you to identify if they're independent or dependent. Let's look at A. It says drawing a card from a deck without replacing it, then drawing another card. All right? If I'm drawing a deck, like a card from a deck of cards, then I'm not replacing it, then my probability of selecting another card changes. Okay, they are dependent on each other. Keyword, without replacing it. Dependent. Drawing a card from a deck, replacing it, meaning I'm putting it back in the deck, and then drawing another card. They're independent events. One does not affect the other. I'm still going to have the same probability the second event. All right, flipping a coin twice. Independent or dependent? If I'm flipping it, does the second time I flip it affect the other time? No.
Yeah.
So they are independent of each other. Flipping a coin and rolling a die, does either one affect the other? No. So they're independent of each other. Choosing a name of the course roster to be president. Choosing another name to be the vice president. Are those independent or dependent of each other? Dependent, very good. Yeah, dependent. Because if I pick somebody to be president, all right, if I pick somebody to be the president, then it's going to matter then who's going to be the vice president. It depends on who I choose to be president. So that is dependent. All right, finishing in first, second, or third place in a 10-person race.
Independent.
Very good, very good. Wait, no, it's not. Oh my God, why are you doing this to me, man? Why are you doing this to me?
It was a 50-50.
It was a 50-50.
like flipping a coin.
Listen, it is dependent. All right, because whoever gets first depends on, then the second place depends on who got first, the third place depends on who got second. They're dependent of each other. All right? It does depend on who gets first. Ruining my video. All right, and then G says choosing a pizza slice and a topping for the pizza. Now, okay, since this is a video, let's go ahead and give you the answer here. Every semester I have people argue on this one. Okay, I see the argument for both. I always say it's independent. A lot of people say it is dependent. So that's a tricky little one there. We'll come back and maybe discuss that as a class. Choosing a pizza slice and a topping for the pizza. They're saying, well, it depends on what the slice is. I don't get it. Personally, I think it's independent. All right, and then H says 75 tickets are in a jar. 3 tickets are selected, one after the other, without replacing the tickets after it's chosen. If I'm not replacing it and my probabilities have changed, it's dependent on each other. Okay? All right, so we've learned outcomes, we've learned independent and dependent events. Good so far? All right, last thing we're going to talk about, and one of the most important things, is the fundamental counting principle. Okay, this is deciding how many possibilities we can have in an independent, dependent event. Okay, so the fundamental counting principle states that if one event has m possible outcomes and another independent event has n possible outcomes, then there are m times n total possible outcomes for the two events together. Let's break that down. Let's do an example. It says that Ryan has decided to buy a pickup truck. His choices include a V6 engine or a V8 engine, a standard cab or an extended cab, and a 2-wheel drive or a 4-wheel drive. How many different possible models does he have to choose from? Okay, we have 3 categories here. We have either the engine he can choose, we have the type of cab he can have, and we have another option of the type of drive he can have. All right, 4-wheel or 2-wheel. The number of options he has for the engine is 2. The number of options he has for the cab is 2, and the number of options that he has for the drive is 2. So the number of possible different outcomes he can have here, the different models, is just 2 times 2 times 2, which is 8. There's 8 different combinations, there are 8 different models you can choose from there. I want to think about it this way. All right, let me explain it this way. All right, so he had 2 types of engines he could choose from. He could either do a V6 engine or a V8. All right, if he chose a V6 engine, he had 2 possible outcomes from there for a cab. Right? He could either do the extended cab or the standard cab. All right, and same thing if he were to choose a V8 engine. He could choose an extended cab from there or a standard cab from there. All right, from there, after those options, he has 2 options after picking those. All right, he can either do a 2-wheel, okay, that's a double lead. This video is great. Either a 2-wheel drive or a 4-wheel drive. 2-wheel drive, 4-wheel drive, 2-wheel drive, 4-wheel drive, 2-wheel drive, or 4-wheel drive. So this tree, we kind of did in our matrix unit, if you remember from Markov chains, this tells you all the different outcomes he could have. He could have a V6 engine with an extended cab and a 2-wheel drive. There's one option. If I were to add up all the options, that's 1, 2, 3, 4, 5, 6, 7, 8 options. That's why the fundamental counting principle works. That's why we multiply the outcomes. And another example of something you can have is a V8 engine with a standard cab and 4-wheel drive. There's 8 different outcomes here, 8 different options. All right, guys, last slide. The fundamental counting principle also applies to dependent events as well, but you must be careful with how you multiply. Let's talk about what I mean. It says, how many arrangements of 3 letters can be formed from the letters of the word math if any letter will not be used more than once? Okay? How many different arrangements of the letters in math? All right, math is a 4-letter word. All right, I have 1, 2, 3, 4 options. Now, how I always approach this with dependent events is I start left and I work my way right. All right, far left in this left spot here, I have 4 different options for a letter. I can either put an M here, an A here, a T here, or an H here. Okay, so I have 4 different outcomes. If I move on to the second letter, then I only have 3 options from there because I'm not going to be using a letter more than once. So in this next spot, I only have 3 options to choose from. The third spot, I only have 2 options to choose from because I've already done a letter here and a letter here. And then lastly, I only have 1 option for here. So that's how you deal with dependent events. Okay, something that's like where you're not using letters more than once. You're not replacing something. Then you multiply. Okay, and then you get 4 times 3 times 2 times 1 is 24. Okay, so there's 24 different ways you can arrange the letters in math. All right, 2 more problems. It says a restaurant serves 5 main dishes, 4 salads, and 4 desserts. How many different meals can be ordered if each has a main dish, a salad, and a dessert? So we have 3 options here. Main dish, salad, dessert. There's 5 options for the main dish. There's 4 options for the salad and 4 options for the desserts. Multiply the numbers and you get the number of possible orderings you can have. 5 times 4 is 20. 20 times 4 is 80. All right, and then the last example, it says, how many different ways can the first 5 letters of the alphabet be arranged if each letter is used only once? Okay, so the first 5 letters, that's A, B, C, D, E, and that's it. All right, so I mean, it's not like actual letters, but it's just basically saying how many different ways can I arrange those first 5 letters in the alphabet, only using them once. So I got 1, 2, 3, 4, 5 options. And in the first spot, I could pick any of the 5 letters. The next spot, I only have 4 choices because I can't reuse the letter. Third spot, I have 3 options. The fourth spot, I have 2 options, and the last spot, I only have 1 option. If you multiply that, that is 120. All right, so we have 120 different ways we can arrange that. All right, if you actually remember 5 times 4 times 3 times 2 times 1, that's actually 5 factorial. But that's all I got. You have a worksheet, front side of the worksheet you'll be working on for homework. I tried to keep this under 20 minutes. I was really close to it, but sorry for any interruptions or any stressful thing like that. If you still don't understand something, I'll go over it in class when everybody's done with the test and everything, re-explain it, summarize it, and then we'll continue with our lesson tomorrow. You guys are awesome. Have a great day.